This timeline represents an assumption that drove policy for decades, the belief that human brain development is complete by early childhood. Recently, neuroimaging proved this false. These curves track neural maturation past adolescence, showing an upward trajectory into the 20s. The teenage brain is an active construction site. It is physically unfinished hardware. Because an adolescent often looks like a fully grown adult on the outside, it is easy to assume their internal processing networks are similarly mature. They are not. This developmental window is defined by a biological process called asynchronous maturation. Asynchronous maturation means that different operational systems within the brain are wiring themselves at drastically different speeds. The systems lagging the furthest behind in this timeline are exactly the ones responsible for higher-order cognition and executive control. This biological delay collides directly with the demands of a 21st-century knowledge economy, which requires precisely those advanced cognitive skills to navigate. Educators trying to teach algebra, judges evaluating youth culpability, and clinicians treating high-risk behaviors are all dealing with this same delayed biology. To accurately predict and influence adolescent behavior, we have to abandon the myth of the completed brain and map out the exact sequence of this uneven neural development. That sequence starts by examining the specific physical architecture of the maturing brain. This cross-section illustrates the foundation. The regions governing basic sensory and motor processing come online early and mature quickly. Next to mature is the brain's reward center, a region known as the ventral striatum. During early adolescence, the ventral striatum undergoes aggressive structural changes, resulting in heightened, highly sensitized activation to potential rewards. Operating alongside this hypersensitive reward center is the system responsible for reasoning, planning, and executive function. That higher-order cognition is seated in the prefrontal cortex. But the prefrontal cortex takes over a decade longer to fully develop, stretching its construction through the teen years and well into the 20s. This leaves the adolescent in a precarious biological state, an intense, highly sensitized reward system operating without a fully formed control center. The neural pathways that connect these emotional centers to the cognitive areas are still physically weak, actively struggling to integrate the two systems. The behavioral output of this mismatch is high-velocity decision-making. Actions surge forward, driven entirely by the promise of reward, lacking the friction of executive oversight. These high-risk behaviors reflect the structural limitations of the brain's current architecture, appearing as a byproduct of development rather than intentional rebellion. The reckless adolescent is a predictable output of an asynchronous system, where the accelerator is fully installed years before the brakes. This uneven hardware dictates cognitive capabilities, particularly when it comes to acquiring quantitative skills. Mathematics, scaling from basic fractions and algebra up to calculus, is a primary domain of higher-order cognition. The difficulty many students experience in learning algebra places a massive processing strain on that still-developing prefrontal cortex. Academic failure in mathematics is frequently a structural issue of neural maturation, rather than an inherent lack of intelligence. Mastering any STEM field requires fluency in the abstract symbolic language of mathematics. This abstract reasoning relies on the exact same cognitive machinery required for a vital, real-world skill, accurately assessing risk and probability. This represents the concept of expected value, the formula used to determine a decision's worth. It shows that value equals probability multiplied by reward. Look at how the adolescent brain processes this equation. The biological reward system links directly to the reward variable. Teenagers calculate that reward potential with intense, magnified biological efficiency. But on the probability side, the equation relies entirely on the underdeveloped prefrontal cortex. The biological hardware required to accurately calculate the probability of negative outcomes is physically unfinished. Behavioral economists refer to the human application of this calculation as expected utility. When expected utility is mathematically skewed by a developing brain, it leads directly to dangerous everyday decisions, like choosing to engage in unprotected sex. An immense overvaluation of immediate reward multiplies against an entirely failed assessment of long-term risk, creating a disastrous behavioral output. From the classroom to the clinic, these varied failures in judgment, whether solving an equation or evaluating a social risk, share a single root cause: the unfinished state of the brain's probability processing hardware. This developmental lag is a critical, extended window of extreme neuroplasticity. This creates the core paradox of adolescence, the vulnerability-opportunity duality. On one hand, this highly plastic, asynchronous state leaves young adults open to tragic vulnerability. It leads to the empirical reality of a 19-year-old college sophomore dead from alcohol intoxication, a direct victim of reward-driven risk blindness. On the other hand, that same plasticity allows for exceptional cognitive growth and resilience. It allows a 15-year-old facing homelessness to survive and eventually enter Harvard University, or a high school dropout to restructure their path and become the U.S. Surgeon General. The darkest pitfalls and the highest possibilities are governed by the exact same biological process of wiring the brain to reason and decide. Because these outcomes are structural, the systems we build around young adults must adapt to this biology. To solve a national college completion rate of just 25%, educators must design curricula specifically for a brain whose higher cognition is still actively forming. The legal system, from social workers up to judges, must weigh this specific cognitive control lag when assessing youth culpability and crime. And clinical psychologists must evaluate high-risk behavior as a predictable interplay between hyperactive emotion and forming executive networks, rather than isolated character flaws. We can harness the immense intellectual potential of emerging adults, but we can only do it if we build our educational, legal, and clinical frameworks around the biological reality of the asynchronously developing brain.